Iya.
Dua.
Saya kami bersyukur makan. Ada tak awal. Saya di Murpulong.
Saya share kat grup akademik tau. Dengan suara awak. Silap. Okay, salam. Okay, tak dengar pun? Dengar? Hello. Testing. Okay, boleh dengar eh? Okay, Assalamualaikum and very good morning. So today we start to discuss a new topic, which is the last topic of this subject, last chapter of this subject, which is the control rectifier. So I believe that you have learned for rectifier in subject power electronics. Do you have subject power electronics? You three? Not sure. You have learned the rectifier. Okay, it's okay. Make sure you have the fundamental on how the operation of the rectifiers. So actually, the rectifier we can divide generally we can divide into two parts or two types. So which is the uncontrolled and controlled, or single phase and three phase rectifiers. Okay. So for this subject, actually, is the extension to study or discuss the rectifiers. So you have already learned the rectifier for single phase, three phase, control and uncontrolled, and the operation of switches, power switches. So if you want to operate the converter as an uncontrolled rectifier, so in this case you have to use the diode. So where diode is you cannot control the switching operation, and so it based on the polarity of the voltage and current to turn on and off. Otherwise, if you want to operate the converter as control rectifier, so you need to employ or apply the thyristor or SCR. And so remember the thyristor SCR, it has three terminals. Remember, so means for uncontrolled, so you must use the diode. So where you cannot control the switching operation. So where the turn on and off based on the polarity of voltage and current. This is the diode, and for the thyristor SCR, it has additional terminal, which is the gate terminal. Okay, so remember here is the anode, this one will be cathode. Anode and cathode, and the additional terminal is gate. So in order to turn on the SCR or thyristor, so this is SCR or thyristor. So it can be turned on when first the polarity of voltage and current must be positive. And another condition must be fulfilled, which is you must apply the current pulse to be injected to the gate terminal here. And so you apply the current pulse to inject to this terminal, the gate terminal. Okay, clear? So it different if you want to turn on the IGBT or MOSFET. IGBT and MOSFET, if you want to turn on, you must apply the voltage pulse and the PWM. Mean the voltage across gate to emitter for IGBT or gate to source for the case of MOSFET. But for the SCR or thyristor, you must apply the current pulse. Okay, so let's start for this week and this class, single phase first. So where we can divide the circuit of single phase into two. So the first using the full bridge. So mean here full bridge, you have 4 diodes. So 4 thyristor, because we concentrate on the control rectifier. Okay, you have 2 leads. So don't forget to put the additional terminal, which is the gate terminal. Okay, so then we can define this is SCR1 or thyristor 1. Here will be SCR number 2, S3, and S4. Okay. Okay, then so you need to identify the important or the input and output terminals of this rectifier. So where the output will be here, right? So this is the output terminal. And the input, you must connect at the midpoint for each lead. So this is the input number 1. And here will be the second input of the rectifier, input number 2. And so you must connect the input terminal to the midpoint of each lead of the rectifier or converter. In general, we can say it as a converter. Okay, where the output, you can connect to the load. So let me draw a rectangular symbol. So where the load, it can be any types of combination load. It can be R load, purely resistive load, resistive and inductive load in series, or RC load, where R, the capacitor and resistor are connected in parallel. So this is the load. Okay, so where the voltage across the load is the output voltage VO, and the current direction must be flow from the positive here to the minus here. And so remember, the load is the passive element. So where the current direction and the voltage must be opposite to each other. So this is the current direction. So since we talk about the single phase, so mean your source will consist of single AC source. So this is a single AC source. Okay. So where this connect to here. So maybe we can put the reference here must be positive and minus. So the voltage here, we can define as Vs. Okay, remember Vs is the sine function. So where Vs, the source voltage, is the sine function, where here will be the peak of the sine Vm. Okay, the amplitude of the sine multiplied by sine omega t or sine theta. Omega t is theta. Okay, so the operation of the converter, SCRs S1 and S2 will be turned on when the source become positive, but they will not conduct until the gate signal applied. So you must know the operation of the circuit. Similarly for S3 and S4. So where they will turn on or forward bias when the source become negative, but will not conduct until they receive the current pulse. Okay. Okay, so this is the first type of the rectifier using the full bridge converter. So in this case, for this type of rectifier, it employs 4 switches, which are SCR or thyristor. And by the part 4 SCRs. For another type is center tap transformer. Okay, ni. So in this case, you need to employ only 2 SCRs. Okay. So for this type of the rectifier, you can you can produce the desired output voltage by selecting appropriate value of the transformer ratio. And so you can step up or step down using the transformer. Okay. Okay, for this subject, actually we focus on the first type here, full bridge, and no need to focus on this part. So this one we have learn or study during study subject for power electronics. So don't need this one. Okay, then we go for the next page. Okay, this is the full bridge. Okay, remember the source voltage is the sine function here. Okay, so firstly you need to know how to sketch the output voltage. So we consider first the load is the R load, purely resistive load. It's not the combination RL or RC, just only R load. Okay, so macam mana how to sketch the output waveform? Okay, let's say here the dotted line here is the this one, sorry, maybe green color, okay lah. So the dotted green color here is the source voltage. Okay, you have here the sine function. Okay, so means the dotted green color is the source voltage, where the source voltage is the sine function, Vm sine omega t. Okay. Okay, so in order to produce the desired output voltage, so you need to apply suitable value of delay angle or firing angle. So remember, so maybe we can define here the green color here. Sorry, maybe use green color is okay. So you must turn on in pairs, mean S1 and S2. You must inject with the same current pulse for S1 and S2. And otherwise for S3 and S4, so maybe this one I use blue. S3 and S4. Okay. Okay, for the sine wave, so you have one complete cycle, right? From 0 to 2 pi. So this is the period of the source voltage, T. And from 0 to 2 pi. So where the T is 2 pi. So mean we can divide the sine function into 2. For the first half cycle and the second half cycle. Half cycle from 0 to pi and pi to 2 pi. Clear? Okay, so for the first half cycle from 0 to pi, so in order to turn on the SCR, so you must turn on SCRs S1 and S2. S1 and S2. So means here, so let's say, okay, sorry, sketch it first, this one. Okay. Okay, then you need to inject the current pulse to S1 and S2. So mean for S1 and S2, sorry. So let me project the line first. Okay, let's say the delay angle or the firing angle for this case, we set alpha is maybe here is 0, right? Here 0. Then here will be what? 5/2, right? 90 degrees. Right? At the middle here, this point at the middle, so maybe alpha is 45 degrees. And so this is the example. Example. So let's say you set the delay angle or the firing angle is 45 degrees. So means for the bottom graph here, so this is the I pulse. I pulse. I pulses. So means from 0 here, this is the 0, then you inject the current pulse here. Okay. So this current pulse for S1 and S2. So you must turn on in pairs secara berpasangan S1 and S2. S1 and S2 receive same current pulse, the green color. Same angle, 45 degrees. So this is 45 degrees. 45 degrees. I just write in degrees. Okay, clear? Okay, then for the another pair, which are S3 and S4. So here use what color? Blue color. So in this case, you need to inject the current pulse at this point, at this angle. So this current pulse for S3 and S4. So where the angle here, this angle, what is the angle here? Should be pi plus in radian. How to convert in radian? So let's say pi is 180 degrees. So you need to convert 45 degrees. So this is the theta. So where the theta in radian, what? 45, 0, pi divided by 180. Clear? So this in radian. So maybe what was the value here? So here will be, is it right? To convert 45 degrees to radian. So means this angle here, this point will be pi plus 45 times pi divided by 180 degrees, right? So this is in radian. Or in degrees will be 180 degrees plus 45 degrees. Clear? So maybe I need to write like this. So this is in degrees. Okay, clear? Clear, right? So mean the gap here will be alpha. So same to here. This gap alpha. Okay, clear? Alpha. Okay, so we design the current pulse first before we sketch the output voltage. So here green color. Right? Okay, once the current pulse is applied to gate terminal for S1 and S2, so mean the SCR will be turned on. So then turn on. So mean these two SCR are in forward bias. So mean these two SCR will be conducted. Okay. So the condition to turn on the SCR, you have two. So the first condition, the polarity of the SCR must be positive. So mean the VS, this case, must be positive. Or current will be positive from anode, flow from anode to cathode of the SCR. So the second condition must be fulfilled when you inject the current pulse. So when you inject the current pulse at angle 45 degrees, so mean these two SCR will be conducted or in short circuit. Clear? So by applying the KVL, Kirchhoff voltage law, so then you can obtain the output voltage. Is it right? So in this case, your output will be what color that I should use? Orange color. So means when you inject the current pulse, then your SCR, sorry, the output voltage initially will be 0, right? From 0 to alpha. Then when you inject the current pulse, these two SCR, S1 and S2 will be short. So then your output voltage will be equal to Vs. You right? So the orange color is your output. Okay. Okay, so this case we focus on the R load. The type of the load is only R load. Okay. So when your source voltage reduced to 0 at pi angle, so mean your polarity will be negative. Your Vs will be negative. So mean inherently, secara semula jadi, inherently, these two SCRs, S1 and S2 will be turned off or in reverse bias. So mean they will open the circuit. Is it right? So means this case your output voltage will be 0 because all SCR block the current. No current flow to the load. So you apply the Ohm's law, so where your VO will be 0. Since your current is 0, the output current will be 0. Okay, clear? So then that's why your output voltage here will be 0 from pi to pi plus alpha, this point. Okay, so then you inject the current pulse to the gate terminal of S3 and S4. Here, you inject to here. Okay. Okay, so these two SCR will be turned on when two conditions are fulfilled. So one, the polarity is positive and not to cathode, and another one is the current pulse injected to the gate. So mean here, these two SCR, S3 and S4 will be conducted or short circuit. So then if you trace or analyzing this circuit, so then you can have the output voltage will be the inversion of Vs. Clear? So this will be 0. So this. Okay, clear? And so you for to turn on the S3 and S4, so this happen when for the second half cycle, you have first half cycle from 0 to pi and second half cycle from pi to 2 pi. So where S3 and S4, you must inject the current pulse for the second half cycle of the source voltage. Okay. So for the second half cycle, your Vs will be negative. Clear? So then by analyzing this circuit and you apply the Kirchhoff voltage law, then you can have the output voltage will be inversion of the Vs. So, inversion of the Vs, minus Vs. Okay, boleh Boleh, Afiq? Okay. So this is for the R load. Purely resistive load. Okay, then you have the outputs, the orange color. The orange color is your output voltage, VO. So where your VO, you can have, or maybe I can write here, sorry, where you can have your VO, maybe I write here VO. It can be two values. So where the VO will be 0 voltage if all LCRs are off, right? All SCR are off, so mean block the current, no current flow to the load. So then your output voltage will be 0. But your SCR will be what? Vs. Actually, you can have 3 different values. First is Vs if S1 and S2 are on, right? This happen when for the first half cycle from 0 to pi radian. From 0 to pi radian. This is for the first half cycle. Half cycle. And during this cycle, S1 and S2 will be turned on when you apply the current pulse. So this case, your VO will be positive Vs. Same. Your output voltage will be same as the source voltage. For the second half cycle, so mean from pi to 2 pi. So this case, you can turn on SCR S3 and S4 when you apply the current pulse, the blue color. So this case, your VO will be what? Positive VS or minus VS? Minus. So you invert the source voltage. So mean this waveform, you invert the wave shape. Okay. So means the VO will be minus VS. Sorry, eh? So your VO will be minus VS if S3 and S4 are conducted, are on. Okay, clear? Okay, so then you can have the output voltage, the orange color here. Okay. So now how to derive the output voltage equation and the average or DC component of the output voltage. Sorry. So this case you need to write in capital letter. Huruf besar, capital letter. Because we get the value is constant, constant value. So in order to calculate the average, so you must apply this definition using this definition where you need to calculate the area first. The area above the time axis, so mean this area, right? For the one cycle or period. Okay, for the output voltage, so what is the period? Is it pi or 2 pi? For VS, the source voltage, your period will be 2 pi, right? Here. Okay. But for the output voltage, the period will be what? Here, right? So this is your period. From 0 to, this is the period, I put T prime. The period will be pi. Okay, clear? Because you can see this cycle will be repeated. Yeah, ni. Cannot get this waveform. One cycle. Then this wave shape will be repeated. Okay, so then we can define the cycle is 0 to pi. Sorry, so maybe we can define the period is for the output voltage is pi. It's not the 2 pi. Okay, pi. So mean here you need to calculate the area, this area. I highlight with the yellow color, above the time axis. How to calculate the area? So you can apply the so where your T now is pi, so you need to integrate, and to calculate the area, you integrate from what? Alpha to pi, right? Alpha to pi. So mean this point is alpha. Okay, because from 0 to alpha, the expression or the equation will be 0. Okay? From 0 to alpha, the output voltage is 0. So then you need to integrate to calculate the area from alpha to pi. Pi, your area ni from alpha to pi. So you integrate from alpha to pi, the function of Vs. Because this case, your VO is Vs. So where Vs is Vm sine omega t, right? Or maybe we can write sine theta. Because omega t is theta. Right? Omega t is theta. Okay, then you can solve for the integration here. So where you can get Vm, you can put offside. Vm divided by pi. So by integrate the sine function, actually you get what? Minus cos theta. Is it right? You integrate the sine function, you get minus cos. Where you integrate from alpha to pi. So then here you can further simplify or solve this equation. Then finally you get Vm divided by pi 1 plus cos theta, right? Okay. Okay, then this is the output voltage. So where you can adjust the output voltage by selecting the right value of alpha. So mean you can control your output voltage by adjusting the theta. Sorry, alpha theta. Sorry, theta. And to obtain the average of the output current, so this one you apply just Ohm's law, because this case we apply only R load, and we just divide by R, or you can write as Vm divided by, and by using the equation above, then you can write the equation of the output. Okay, okay, this is the output voltage, the average component or the DC component. So mean you can mean your wave shape will be constant value. So that's why I put in capital letter, because this is the DC component. Okay, any question? Okay. Okay, then for the RMS, how to calculate the RMS? So remember to use this equation. Ni. Last year kan? Semester 4 So in order to calculate RMS, so actually you can write in general. So actually this equation comes from here. So the RMS value, maybe RMS. So actually is you square all this term where this is 1 divided by T, the period of the output voltage or the current, the RMS current, sorry, the current. You integrate from alpha to pi. So where this your output, your output function, I squared. So then you integrate with respect to theta, d theta. Okay. Okay, clear? Okay, then you can finally you can get this equation. So where the RMS is determined by the delay angle, alpha. So you have alpha here and this one. By selecting appropriate value of alpha, then you can obtain the desired value of RMS current. So you have to take note for the rectifier where the RMS current in the source, so mean the source here your RMS. So maybe I can put here as the RMS, IS RMS. So actually the RMS current for the source are equal to the RMS current of the output current. These two current are same. RMS of for the output and for the source. This one you need to take note. Okay. So then how to derive this equation? So you can see the derivation from the next page here. So this is the way you derive the equation. Okay, so for the case of R load, so remember this case we apply for the R load, a purely resistive load. So maybe you can change this one as IO. So where your IO, because so means so the SCR will be conducted S1 and S2 at this point. So then your VO will be equal to VS. Is it right? Then you will turn off. Your VO will be 0. Then this case at this point, your S3 and S4 will be conducted. Okay. Okay, to sketch the output current for the case of R load, so where you can actually the wave shape will be similar. Is similar to the output voltage wave shape. And because this is for R load, so means the amplitude, sorry, the peak of the output current here will be what? Vm divided by R. Okay, clear? So this is your output current, IO. It's not the output voltage. The wave shape is similar, same. But the magnitudes are different. The instantaneous value are different because you need to divide by R, the resistance. Okay, to derive the RMS, so you need to apply this equation. So you have to need to square root all this term 1 divided by T. Then you integrate from alpha to pi, the current function here, IO, with respect to theta. Then we know that the IO, so your IO, sorry. Okay, we know that your IO, so IO actually is your VO, right? Sine omega T divided by R. So where your VO is Vm, sine omega T per R. So then you can substitute to here. You substitute to this term. Clear? So then you get here, this one. Okay, then you can further solve this equation. So you need to apply the trigonal. So you see the trigonal identity. So where you can write the sine squared theta as 1 divided by cos 2 theta divided by 2. So please look at the trigonal identity. You can search from Google. Okay. Okay, then you substitute. So then you can integrate this. So this one you just apply the mathematics because this is not the mathematics class. So you can refer to the the related subject the mathematics mathematics engineering, right? Mathematics engineering. Maybe you need to apply the trigonal identity. You need to apply the rule of proportion, a rule of chain. I don't know, rule of chain. So then actually you can further solve this one. Then finally you can get. Okay. So this is the way how to derive the RMS output current. Okay, I believe this process to derive you have already learned in power electronics subject last year. Okay. Okay, then we go for the exercise. This is for the exercise number 1 before we take a break for 10 minutes. Just simple exercise, very straightforward exercise. Okay, so exercise number 1, full wave bridge rectifier. The AC is 120 volt RMS, also given value in RMS. Frequency is 60 Hz, load 20 ohm. The delay angle alpha is 40 degrees. So you need to calculate the average current in the load, power absorbed by the load, and the source volt amperes. Okay, to calculate the average output voltage, so you need to use appropriate formula or equation. So this is the equation of the output voltage. You just plug in based on the information given in the question. Where this case, the alpha is 40 degrees. Your VM. So firstly, you need to calculate the VM here, right? So where your VM is, the RMS value is 120 is RMS. So you need to apply with the set 2 here. Okay, clear? Okay, then you get the output is 95.4. The current just divide by R, because this case we apply only R load. You just apply you divide by R, where the R is 20 ohm. Okay, clear? Then to calculate the RMS, for the RMS, so here is VM is 120 in RMS. Then you need to multiply by Z2 to get the peak or the VM. Divide by R, where your R is what? 20 ohm. Then you square 1 divided by 2. Okay. So this one you need to careful because you have alpha here. So your alpha calculation in radian or degrees? Degrees or radian? So based on the question given, the alpha is what? 40. Yeah, 40 degrees. Alpha is 40 degrees. You must substitute in radian or degrees. So you must substitute in radian. So mean you need to convert first the alpha in degrees to radian. So macam mana nak convert to radian? 40 degrees multiplied by what? Pi. Divide by 180 degrees. So must be in radian. So this one in degrees. Okay. So then you get someone calculate alpha in radian. Ya lagi ke? Okay, sikit lagi. Alpha in radian 0.698 radian. 0.698 divided by 2 pi. So then you plus sine Okay, this one also you need to careful. So make sure you set the right mode in your calculator, for your calculator, in radian or degrees. So if you set in degrees, so mean you need to put here 2 times 40 degrees. Right? And based on your calculator setting, radian or degrees. But if you set in degrees, radian, so then you must multiply by alpha in radian, 0.698. Then divide by 4 pi. Then finally, you can calculate the RMS current as 4.8 ampere. Okay. Okay, please careful to calculate ni alpha here and the sine function here. Okay, RMS current. So we calculate the RMS current in order to calculate the power absorbed by the load. Okay, because the question here, you need to calculate the power absorbed by the load. So that's why you need to calculate first the RMS load current. Okay, to calculate the RMS load currents, so here is your RMS, the output current, the RMS output current squared multiplied by R. So here is 4.8, 20. Then you get the power must be in watt, 673 watt. Okay, the apparent power, S. Apparent power, So the apparent power is multiplication between the source, because here is source. So remember the output of RMS, so actually is IRMS, based on here, RMS. So will be equal to RMS current of source. Okay, so you have to take note this one. So mean here, since S, the apparent power is multiplication between the VS RMS and IS RMS, right? So where your VS RMS based on the question given is what? 120. Then you multiply by 673. Then you get the value will be 696. The unit must be VA, volt ampere. ISR? Oh, 5.8, sorry. 5.8. Okay. Okay, and the power factor. So you can calculate power by using this equation where the power factor is the ratio between power and the apparent power. Okay. So where P is 673 watt divided by 696. Then you get 0.6967. And unitless. So what is the purpose of calculate power factor? Someone can give the reason we calculate power factor. Apa dia? Abrar. Saida. P. What is the purpose we calculate the PF, power factor? Right? Okay, please find the answer. Give me the answer next class. Okay. Okay. Okay, then we can take a break. 10 minutes. Now is 9:15. 9:25, the start class. Okay lah.
Kita kena elak penalty.
Ah,
Tinggi.
ya. Okey, sikit je boleh. Okay. Ready semua? Okay, let's move to new section of this topic. Okay, section 4.3. So now we discuss where the load now is combination of RL and the source. RL and source. So where the source is the DC voltage. So in practice, we can represent the DC voltage here as an array of solar panel. Or the batteries, the set of batteries which are connected in series. So you have the SCR for the control SCR. We apply the SCR. You have 4 SCR here: the source voltage, where these 3 elements R and the DC voltage source are connected in series. So we need to define the output voltage VO is the voltage across this point to here, plus to minus VO. And the current IO, where the current flow through these 3 elements, RL and DC source. Okay, so for this case, the load consists of L. You have L now, the inductor. So where the inductor is one of the energy storage element. So you must understand the behavior of the current when flow through the inductor, where the current cannot immediately change, same as the voltage. Yeah, and the behavior of the inductor current, because the current need to be charged and discharged. Sorry, it need to increase in exponentially or decrease in exponentially. It cannot immediately change as the voltage wave shape. Okay, so remember the inductor is the energy storage. So mean you need to for a time for it to store the energy and release the energy. Okay, and same as the capacitor. For the inductor, the effect on the current, where the current cannot be immediately changed. For the capacitor, the effect on the voltage, where the voltage of the capacitor cannot immediately change, because the voltage of capacitor need time for it to increase or decrease in exponentially. Okay, so first let's sketch, because we need after this we need to derive the output voltage, the average output voltage VO. So before we derive the equation of the output voltage, so you must know how to sketch the output voltage VO. Because from the wave shape, then we can derive the equation. Okay, so this is what? Okay, firstly maybe we try to sketch the source. So remember your VS. Maybe here I put the blue color. Sorry. VS green color lah, or red color, sorry. So where your VS is the function of sine, right? Vm sine omega t or sine theta. It means here you can draw the source voltage. I put the dotted line here, dotted line. Okay, so this is your source. Okay, this is for the first half cycle from 0 to pi. Then for the second half cycle from pi to 2 pi, so you can have the negative, right? Because this is the sine function. Okay, and the red color, dotted red color is just your source, and the dotted is source. So maybe we can extend for the next cycle. And cycle number 2, from 2 pi to 3 pi is positive, and from 3 pi to 4 pi is negative, due to the sine function. Betul tak? In this case, your VM is, sorry, your peak of sine is Vm. So this is Vm. So this is Vm. Okay, the peak of sine is Vm. Okay, so maybe we can set the alpha. So let's say this case, for example, for this case, we set alpha same as previous, which is 45 degrees. So this is the example. So mean maybe we can, sorry, I just put the dotted first. I mean, it should be where? So here is 0, right? 0 start to build up the sine. So mean the peak of sine here will be pi per 2, right? 90 degrees. So mean your 45 degree will be somewhere else here, right? So this is the point. Okay. It means here, this point, and here. Okay. Okay, let me sketch the projection line first for these 4 points. Grey color. Okay. Okay. Okay, so means here will be time is 0 and 0 or 0 time or 0 radian and 0 degrees. So where we can set or define the alpha will be at this point, right? So this is your alpha. So when at angle alpha, we inject the current pulse. And current pulse to turn on, which is SCR. S1, S2, S3, S4. So remember the turn on must be in pairs, secara berpasangan. So it means you need to inject to the gate pulse of S1 and S2. So you inject the current pulse here. Same current pulse to S1 and S2. So it means here you can sketch the current pulse will be here, right? So this is your current pulse. Okay. High pulse. So this is for S1 and S2. Okay. So then for the first half cycle from 0 to pi, so you must turn on S1 and S2. So you inject the current pulse at alpha. So this case, when the current pulse is injected to these terminals, these two terminals, so where your VO will be what? Your VO will be equal to VS. Initially, sorry, so maybe we start from here, this point. Your VO, the what color? Maybe the orange color is okay. So VO will be equal to VS. Is it right? VO equal to VS. So this case, maybe we can sketch from these two interval. So actually, SCR, S1 and S2 are turned on. So then you can see the conduction angle will be extended, right? Beyond the pi. Because of what? Someone can give the reason why the conduction angle is extend from pi to this angle. Because of the energy storage element, the inductor. Okay. Okay, where when these two SCR are turned on, S1 and S2 are turned on, when you apply the current pulse, the green color here, so means these two switches, S1, S2 will be conducted from alpha to pi plus alpha here. So this point is what? Here will be pi plus alpha. So you can see here. So then here, the output voltage when SCR, S1 and S2 are turned on. So then you can see they have negative area here. Because of the inductive load. Okay. Clear? So S1 and S2 are conducted when the angles between alpha to pi plus alpha. Yeah. From alpha to angle pi plus alpha, these two SCR will be conducted, S1 and S2. Because of what? Because this case, we assume that the load current is continuous here. The load current is continuous due to the inductive load and steady state. So yeah. So mean here you can sketch the current. The current profile will be something like this. Maybe I use what color? Blue color. So mean here when the S1 and S2 are turned on, so maybe your current start to build up at this point here. So then it will be charged. In this case, the current will be charged. Okay. So then when your current your source voltage reduce to 0 and negative, here the current will be discharged to this point. So this is the profile of your load current, IO. And so remember, your inductor current cannot immediately change. It cannot immediately change, same as the voltage, the source voltage or the output voltage. It requires time for it to charge and discharge. Sorry, to increase and decrease in exponentially. So remember, this topic you have learned already in power electronics subject and last year. So you must know the behavior of the inductor current. And it's not same as the R load. For the case of the R load, only R load, where the wave shape of current and the voltage will similar. Okay. Okay. So means this is your output current. Okay. Then for the second half cycle, pi to 2 pi. So this case you can conduct which switches? S3 and S4. So this one maybe I use what color? Indigo. So here you can inject the current pulse at pi plus alpha. Okay. So means this current pulse you inject to the gate terminal of what? S3 and S4. So mean you inject to here S3 and S4. S4, same current pulse. Then these two switches will be conducted. So when these switches are conducted, so then your output voltage will be equal to what? So in this case I use orange color. So means suddenly your output voltage from 0 change to this point. Same to here. Okay, same to this point. So then your output will be equal to this line. Okay. And the conduction angle will be extended to 2 pi plus alpha. So means here. Okay, right? Okay, so means for this case, from pi to alpha to angle 2 pi plus alpha, SCR turn on are S3 and S4. S3 and S4. So mean for this case, your VO, for this range, your VO will be what? Someone can give. VO is minus VS. And for the case of S3 and S4 are turned on. For the case for S1 and S2 turn on, VO will be equal to what? Positive VS. Yeah. So mean for S3 and S4 turn on, so your output voltage is equal to, you invert the source voltage waveform. You try to invert the source voltage waveform. So there I put negative sign here and minus sign here. Okay. Clear? So mean here your current is continuously charge and discharge. Which color? Blue color. So then when your S3 and S4 is turned on, so then your inductor start to charge, store the energy. So mean your current increase in exponentially. When your voltage, the orange color voltage start to reduce and goes to negative value, so mean the current will be in. So the current will be decreased. Go to where? Go to here, right? Okay. So mean this case your current will be continuous. It's in continuous. Mean your current is not reduced to 0. I did not climb to 0 and then suddenly positive climb to 0. That one is discontinuous. This case, when you put the inductor, your current is always positive and continuous. So means this current, because the flow of current, it will force these two SCR to be conducted. Even though the polarity of the voltage across two SAR are negative. Right? Okay? Because of the current will force two SCR to be conducted. Okay. So then here S3, S4 turn on, then this process will be repeated. So you can sketch to completely sketch the waveform here. Then it will increase to this point, this point. Then here VO will be equal to positive VS when S2 and S2 are turned on. Then here S3 will be turned on. S3 and S4 will be turned on. Okay, this process will be repeated. It means at this angle, S1, we inject the current pulse to the gate terminal of S1 and S2. Then this, we inject the current pulse to S3 and S4. Okay. I mean, here will be what? This angle will be 2 pi plus alpha. Here will be 3 pi plus alpha. Okay, so mean this gap are same. Alpha, here will be alpha. This one will be alpha. And same goes to here. Okay. So you must understand the nature or the behavior of the inductor current. So where your current will be continuous. Because of the flow of current, it will force the SCR to conduct. Bye. Okay, so means here maybe we can extend the sketch of the current here. So start from here lah. And same goes to the output voltage. Which one? Here, right? Start from here. Okay. So we consider the wave shape already in steady state. Okay, then the orange color is your output voltage. Okay, so in this case, your output voltage can be two, right? So one is positive VS, right? If what? S1 and S2 conduct, right? Otherwise, your VO is inversion of source voltage, VS. If S3 and S4 are in conducting mode. Okay. Okay, then based on this sketch of the output voltage waveform, then you can derive the equation of the output. How to derive? So we apply the same thing. So you need to calculate the area. So maybe the carrier now will be here. Sorry. So this is your area. You have the positive area, right? And the negative area here. So maybe we define the period will be here, right? So this is your period now. Is it right? This is your period. T. I put T. Because this wave shape will be repeated. So we define the period from this point to here. So it's not 2 pi. So actually your period is same as the previous, which is pi. Okay. So means the area you have the positive area and the negative area here, negative area. So in order to calculate the area, so before that T is pi. So we agree that the T is pi. Then to calculate the area, you integrate from what? You not integrate from where? Alpha, start from alpha here, this point to this point, right? So alpha to pi plus alpha. So where the function of VO will be VS. The VO is VS for the first half cycle here. VO is VS. So your VO is VM sine omega t or sine theta with respect to theta. So then you can solve lah the equation. So then you here Vm you take out Vm divided by 5, you factorize kan, you integrate the sign, you get minus cos theta. Alpha to pi plus alpha. Then finally you get, is it right? Oh, okay. Because you have pi plus alpha here. Okay, sorry, this actually you can get the final equation will be 2Vm divided by pi cos alpha. Okay, during you solve to get the last equation, so actually you need to apply this theorem and this trigonal identity. So where you can have this one, right? Cos pi plus alpha here. So where cos pi plus alpha actually is cos pi cos alpha, right? Then here will be minus or positive? Minus sin pi sin alpha. Sin pi will be 0. So then finally you get cos pi will be minus 1, right? Minus 1. Then you get negative cos alpha. So you apply this identity. So actually then finally you can get this equation and the final equation here. Yeah. I don't need to show this one. This is not the mathematics class. We just apply the concept. 9:47. Okay, clear? Right. So maybe next week we complete this topic. See, okay, good. Next week. Okay, then here, actually, to study this topic, this type of the rectifier, so you must able to calculate the average of load current here. So this one simple, you just apply the basic theorem, electric circuit. So where the I/O, the current flow to the load. So actually you can in order to get this equation, firstly you need to neglect the effect of inductance because this is the DC analysis. The L we can assume 0, no effect of L. Okay, clear? So mean here you can have from this circuit actually you can simplify the circuit. This one will be VO. You have the resistor, right? And was plus minus VDC. So this is only R. You neglect the effect of inductor. So then from this you can calculate the output current by applying the basic circuit theory, electric circuit theory. Voltage divider, Ohm's law, that one, Kirchhoff voltage law. Then you can get this equation. Simple, No need to explain this one, Okay, then to calculate the power absorbed by the DC voltage, so mean here, the power absorbed by the DC voltage. So mean this case you want to operate the bridge converter as a charger circuit. So mean your power you deliver from the AC source to the battery. The battery absorb the power, because we want to charge the battery. So where the power absorbed can be calculated using this equation. Simple, straightforward, by multiplying the current flow through the battery and the DC the battery voltage VDC. Okay, Lepas tu then power absorbed by the resistor. Ni simple, straightforward. I squared multiplied by R. So this case we need to assume that the RMS of the output current or IRMS equal to IO. Okay, so we can consider the current is no ripple, ripple free. So that's why we can equate these two terms, IRMS and IO. Okay, then we can proceed to do the exercise. Simple exercise. For the exercise, so this case you have the RMS input voltage and source voltage at 60 Hz. The DC voltage is 100 volt. R is 5 ohm. Then you need to consider the inductor is large enough to cause the continuous current. Okay, you have two parts here. First, you need to determine the delay angle such that the power absorbed by the DC source is 1 kilowatt. And the second part is to determine the value of L, so that you can limit the variation of current. In other words, the current ripple of the output current. You can design the L, what value you need to put here in order to limit the current ripple, the output current ripple. Okay, you have two parts in this question. Okay, so we go one by one. Okay, in part one, part A, given the DC voltage, the power absorbed by the battery here, you have the power absorbed into the battery here is 1 kilowatt. So where the PDC is the multiplication between the battery voltage and IO, right? Battery voltage and IO. So then from here you can calculate the output current. Simple Ni. You calculate the output current IO. PDC is given 100 volt. And the PDC given as 1 kilowatt. So then from here you can calculate the output current. Very straightforward. You get 10 ampere. Then you need to calculate what? You need to calculate the output voltage produced from the rectifier, the VO. Okay, you nak calculate at VO. So to calculate VO, so you can apply this equation. So mean you can represent or simplify the circuit as, so let's say you have the battery here to represent the output voltage. You have the resistor and the battery, the DC voltage source. Here is the VDC 100 volt. So you have R and the calculated current. And you represent the output of the rectifier as the battery voltage, battery symbol VO. So from here you can calculate the VO using the what? And Kirchhoff voltage law. Is it right? So where the VO is the summation between the DC voltage 100 volt plus IO and R, IOR, multiplication between IO and R. Okay, then you get 150 volt. The output voltage is positive. Okay, after you calculate the VO, you need to calculate the required delay angle, the alpha, and the firing angle. So you can apply what equation? This equation, right? You apply this equation where VO is 2Vm divided by pi cos alpha. So you rearrange this equation to solve for alpha. Just substitute all the information given, then very straightforward, then you can calculate the angle. So you can provide the answer in degrees or in radian. It's okay. So don't forget for the calculation VM, so you need multiply 240 by 2 to calculate the peak, the amplitude of the sine, VM. Simple very simple So then next page. Okay ni. Please understand this one. Okay, because in part 2, in part B, the question given asks you to calculate, determine the value of L here, so that the current variation can be limited to 2 ampere. So the output current will be something like this, this one, this wave shape. This is your output current. Sorry, I complete this sketch. The output current IO. Here is your IO. So your IO discharge and charge, and your inductor will be charged. Discharge decrease, exponentially increase and exponentially decrease, and here will be increase, decrease, and increase, decrease. So this is your output current and the variation of the output current. So mean by applying appropriate value of L, you need to design the value of L so that the ripple, the ripple here. So mean the difference between the maximum to the minimum here. Okay. So means this. The change of IO. So you need to design the value of L so that the current ripple limited to what? 2 ampere. Okay, clear? So ini. So this is the maximum value. Here will be the minimum value. So the current ripple can be calculated as the difference between the maximum output current and the minimum output current. IO max minus IO min. Okay, so this part you need to calculate the value of L so that you can limit the current ripple. Okay, so mean here. Yeah. So this case, you read this statement. Variation in load current is due to the first AC term. So you must understand this one. The first AC term. So what is the first AC term of the rectifier? N equal to what? N equal to 1, 6, 2, 3, 4, 5, 6, 7. By looking to the wave shape of the output current, so actually you can you know lah what is the first term of the output current. There. So remember to write the expression of the output IO. So you can write in Fourier series. This one you have learned in power electronics subject last year, where your IO summation of the average component plus the harmonic component, right? You need to sum starting from the first harmonic and what to infinity. So maybe here will be IN. So this one I don't know the function, maybe cos or sine here. To get the blue color waveform, the blue color waveform IO, so actually you can express the output current in Fourier series, which is the summation between the DC component IO and total of harmonics component. Yeah. So the first harmonic component will be what? N equal to 1, 2, 3, 4, 5. 1 is the DC. Sorry, 1 is not. Actually, you cannot say 1 because 1 is frequency at the fundamental frequency 50 Hz. Because this is the rectifier. No N equal to 1. Actually, you have N equal to 0. To mean the first component, the DC components located at which frequency? 50 Hz, 60 Hz, 0 Hz. This is basic. You learn in Fourier series subject kan, Fourier series topic. You look at of the DC current, the blue color. So mean from here you can get the average, the DC component. So where the DC component, if you draw in the Fourier series frequency spectrum, the DC component is located at 0 Hz. Is that 0 Hz? And kalau you ada Fourier series here, this is frequency. Here will be your N. So the first component is the DC component, which is located at 0 Hz or N equal to 0. Or the N is the order of harmonic. And the first AC term, I what? IN. Where N equal to what? You can see from the wave shape here. If N equal to 1, the frequency will be 60 Hz. So let's say we apply the source is 60 Hz. And N equal to 1. So the period will be from 0 to pi, right? But this case, for one complete cycle of the source, you have 2 complete cycle of the output waveform. So mean your frequency will be 120 Hz. So mean the first harmonic appear at N equal to 2. N equal to 2. So N equal to 2. So mean here will be I2. So this component will be I2. Because you have 2 complete cycle of the output wave shape. voltage or current kan. For one complete of the source voltage Vs. Nampak Vs awak ni. From 0 to 2 pi. From 0 to 2 pi, you can have two complete cycle of the output voltage or output current. To me, you can say your n will be 2. The first harmonic is appear at for n equal to 2. So n equal to is the first harmonic component. Sorry, I2. I2 or V2. Boleh tak? Okay. Okay, so means here, okay, the first element is the first acetylene will ni. So mean here, sorry. Okay, so mean the first current component will be I2. So where I2 is the ratio between V2 and Z2. So you can write from, you can obtain this equation from the general equation, which is In is Vn divided by Zn. So this case n will be equal to 2. The first AC term or the first AC harmonic, sorry, the first harmonic component or the first AC term, n will be equal to 2. So this one is 2. Okay, where V2, okay, this case important, V2 is the first voltage harmonic component, which can be estimated from the graph below. So this graph is given here. So then you can see from the bell curve ni, you have n equal to 2. So this is the first harmonic. First harmonic. Then the second harmonic at n equal to 4. If your frequency is 60 Hz, so then you need to multiply by 4. 240 Hz. Then the third harmonic n equal to 6. Fourth n equal to 8. Okay, so actually you can sketch this characteristic apa kan, based on the equation and that you have learned already in power electronics subject. And for this subject, I no need to discuss in detail how to get this characteristic. We just apply. Okay, just apply. Okay. Okay, so based on the calculation of alpha here, so you get alpha is 46 degree, right? So then from here, based on the graph, you can estimate the V2 and the first harmonic. So mean you need to apply this curve. You just focus on this curve. So where your alpha will be, here will be 40, mean here will be 60, right? 46, something somewhere else here, right? So this alpha is 46 degrees. So you take out your ruler, then you sketch the punya line, projection line here. Okay, then extend to here. For the y-axis, and this y-axis actually provide the information of Vn divided by Vm. So mean this point, maksudnya you get, you based on your calculation alpha 46 degrees, so you draw the line here, touch to this curve, and n equal to 2, then you project to this point, right? So actually here, this point, you can estimate the value of V2 because we concentrate for N2 curve, right? So V2 divided by Vn, which is equal to what? 0. What? 0. Here will be 0.7, right? 0.6. 0.68. Okay? Apa dah? Dah pukul 10 dah. Sikit. 0.68. So then here, so from here, you can calculate your V2, right? V2. So your V2, so we get V2 is divided by Vm, which is equal to V2 divided by your source voltage in RMS is 240. You need to multiply by Z2. Then here we can approximate based on from the graph, you get the value is 0.68. So then from here, you can calculate for V2. Okay? 0.68 multiplied by 240 set 2 equal to what? 230.8 volt. Okay? Okay, then for impedance Z2, because you need Z2 is what? Z2 is, because this is the combination of R and L, so actually you need to calculate the magnetic value of this rectangular and omega L. So where you can calculate the magnitude R squared and omega L squared, right? Okay. So where here you just substitute the value R is 5 ohm. Sorry, so please take note your N is 2. N is 2. You multiply by omega 2 pi F. Frequency is what? 60, 60 hertz. And L. So we need to solve for L here. Okay, then from here you can calculate L. The required L. So where? Okay, next page, sorry. So the required load impedance for N2 is then V2 divided by I2. So your V2 based on the estimation is 230 divided by 8 volt divided by, this one is what? I2. This based on the design specification given. So this part of question you need to calculate the value of L, the suitable value of L in order to limit the current ripple. Your current ripple tadi, here is your current ripple, right? So where you need to limit the current ripple, change of IO 2 ampere, right? Okay, so this is the AC component. Okay, so means the first AC term I2. So maybe you can, okay, so this is your IO. By applying the Fourier series, sorry, maybe I can illustrate from here, sorry, just to illustrate you to understand what is the definition of Fourier series. So this is your IO. So your IO will vary from peak to peak. So our aim now to limit the current ripple to 2 ampere. Okay, so remember, based on the current wave shape, you have the average. So the average something here, right, like this, the orange color. So this is your DC component or the average. So where your current wave shape here, IO, so actually is the, when you apply the Fourier series, is the summation between the DC component and the total harmonics component. Starting N equal to 2, you calculate to infinity. So you can refer to the textbook and the function of equation in the bracket. Okay. So means the variation based on this Fourier series, we can say that the variation is mainly determined by the first AC term, which is I2. So we can say that this one to produce the IO is the summation of the average term, the DC component, right? Plus the first AC term, which is I2 here. Is it right? So we ignore the higher harmonics component, I4, I6, and I8 until infinity. That one, because the value are too small, then we can neglect. So we can say that the variation or the current ripple is mainly determined by the first AC current, which is I2. Nampak? So kan, kalau you based on this equation, the Fourier series here, is the summation between the average component here, you plus with the first AC term, I2. Where the higher harmonics component, I6, I8, we ignore. Because the value are too small. Okay? So mean the current ripple, because the design they required, the current ripple must be limited, the current ripple at 2 ampere. So means we can say that the peak to peak for I2, the change of I2 also 2 ampere. Betul? You boleh imagine you summing these two wave shape, the average and the AC term here, the first AC term I2. So actually you can get this wave shape. Ini you belajar Fourier series tu. Okay. So means from here you can obtain your I2 will be the peak, right? I2 ni. This is your I2, the peak from 0 to peak of current. Clear? So what the value of I2? Peak to peak is 2. The peak will be the change of I2 divided by 2, which is 1 ampere. So then from here, you can substitute to here. P2 is 230.8. Based on the estimation from the graph, you divide by 1. Then you get here is 230.8 ohm. Okay, then you can compare. We try to simplify our analysis. Means you can ignore the effect of R. Since your R value 5 ohm is too small. 5 ohm is too small compared to the total impedance. The total impedance, which is 230.8 ohm, which is the required impedance. Okay, so in this case, you can you apply this equation. Okay, this equation and this one. So you can ignore this term. You can ignore this term because R value is too small. So then from here, you can calculate the R. Sorry, the L. L pula. So where L is Z2 divided by 2 omega only. And because R you neglect because R is too small compared to the total impedance. Okay. So mean here Z2 is what? 230.8 divided by 2, where omega is 2 pi 60. Then from here you get L is 0.305 Henry. Finish. Okay. Ada kelas ke lepas ni? Ada kelas? No class after this? Ha? Ha? Ada? Boleh keluar. Sorry ya. Tu pensyarah awak kat sini. Kosong. Okay, please try to understand this one because we can apply the same concept for the three-phase inverter, three-phase rectifier, three-phase control three-phase rectifier. Your final exam will be something like this. The question and the shape of the question will be something like this. Okay. Okay. All right. Thank you. See you next week. Empat tunjuk simulation. Yeah. 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 Recording. Yeah, record.